sklearntree. Description. Decision trees are a powerful machine learning algorithm used for both classification and regression tasks. They create a tree-like structure where each internal node represents a feature or attribute of a data, and each branch represents a possible value of that feature. The tree is constructed in a top-down manner by recursively partitioning the data based on the most informative features. This process continues until the leaves of the tree are reached, which represent the final predictions. Inputs. Feature matrix: a dataset containing numerical and categorical features. Each row represents an instance, and each column represents a feature. Target variable: the variable that the model aims to predict. For classification tasks, this is a categorical variable, while for regression tasks, it is a continuous variable. Outputs. Prediction: the predicted value for the target variable for a given input. Decision tree model: the trained decision tree structure, which can be used to make predictions on new data. Steps. Data preparation: this involves cleaning and pre-processing the data, including handling missing values, transforming categorical features, and scaling numerical features. Tree construction: the algorithm recursively splits the data into subsets based on the feature that best separates the instances into different classes or values of the target variable. This process continues until the leaves of the tree are reached, which represent the final predictions. Pruning: to prevent overfitting. The tree is often pruned by removing branches that do not improve the model's performance on a validation set. Metrics. Accuracy for classification tasks. This measures the proportion of correctly classified instances. Precision: this measures the proportion of positive predictions that were actually positive. Recall: this measures the proportion of positive instances that were correctly identified as positive. F1 score: this is the harmonic mean of precision and recall. Mean squared error (MSE) for regression tasks. This measures the average squared difference between the predicted and actual values. R squared for regression tasks. This measures the proportion of the variance in the target variable that is explained by the model. Visualization plots. Decision tree diagram: this visualizes the decision tree structure, showing the features, splits, and predictions at each node. Feature importance plot: this shows the relative importance of each feature in the decision tree. Fine-tune parameters. Max depth controls the maximum depth of the tree, limiting the complexity of the model to prevent overfitting. Min-sample split specifies the minimum number of samples required to split an internal node. Min-samples leaf specifies the minimum number of samples required to be at a leaf node. Criterion defines the splitting criteria. Common options include Gini for the Gini impurity, which measures the probability of misclassifying a randomly chosen instance, and entropy for information gain, which measures the reduction in uncertainty after a split. Uncertainty methods. Confidence interval: the prediction interval provides a range of values that are likely to contain the true value of the target variable. Out-of-bag error for random forest models, which are ensembles of decision trees. This is an estimate of the model's error based on the data that was not used to train each individual tree. Challenges and fixes. Overfitting. Sample use case that resulted in challenge 1: a decision tree trained on a dataset with a small number of instances may overfit to the training data, leading to poor performance on unseen data. Fixes to challenge 1. Use techniques like pruning or regularization to prevent the tree from becoming too complex. Use cross-validation to evaluate the model's performance on unseen data. Sensitivity to noise. Sample use case that resulted in challenge 2: decision trees can be sensitive to noisy data. where outliers or irrelevant features can significantly impact the tree structure. Fixes to challenge 2. Clean the data to remove noise and outliers. Use feature selection techniques to identify and remove irrelevant features. Interpretability. Sample use case that resulted in challenge 3. Very deep and complex decision trees can be difficult to interpret, making it challenging to understand how the model arrives at its predictions. Fixes to challenge 3. Use visualization techniques to help understand the tree structure. Limit the depth of the tree to make it more interpretable. Data imbalance. Sample use case that resulted in challenge 4. If the data is imbalanced, meaning that one class is significantly more frequent than others, the decision tree may favor the majority class and perform poorly on the minority class. Fixes to challenge 4. Use techniques like oversampling or undersampling to balance the data. Use metrics like F1 score or AUC to evaluate the model's performance on both classes.